Mic check, mic check, mic check, mic check. Hello, everyone. Thank you for joining. My name is Ife Wichomeke, founder and lead DevOps engineer here at Nimbus Compute. So today we are going to explore the new reality of AppSec, specifically real-time malware detection in open source package. So we all know modern apps rely heavily on open source. That's a game changer for security. Open source now forms up to like 90% of the code in a typical application, which brings incredible benefit in innovation and also in speed. But it also expands the attack surface for bad actors. So we can no longer assume that our software supply chain is safe by default. So looking at the title here, the real-time malware detection in open source package is a hint at our focus. We'll discuss what we need to catch like malicious code in real time as it tries to enter our development pipelines rather than long after the fact. So on the second slide, 95, I would say 97% of commercial application use open source components, and each app uses hundreds of them on average. So it's not unusual to have like 500 plus open source library in a single application. In other words, open source isn't just it's not common. It's the foundation of our software. We see over 30% year over year growth in contribution to open source projects. The ecosystem also booming more packages, more updates, more dependencies, all in community maintained code. So this means that new code is flowing into our product faster than ever, which is, I would say, which is like a double-edged sword. However, this resilience comes with risk. So roughly 75% of application we are seeing contain high-risk vulnerabilities in their open source components. Even non-vulnerability are widespread. Now, consider unknown malware sneaking in. This is a serious risk. So attackers have now noticed the resilience on open source software. Malwares targeting open source packages have surged by like 633% in 2022, and then grow another 245% in 2023. That is an explosion of attack, all aimed at open source supply chain. Now, the question here is why attackers are targeting open source softwares. Now, here's the thing: attackers goes where the opportunities are. If 90% of the code in app is open source software, that's a huge attack surface. So instead of like breaking down the front door with an exploit, they can slip in through a side window, uh, an open source package that everyone actually trusts. So I'm going to use this analogy for an example. So think of building software like you are cooking. So you use ingredients from all over the world. So even if one ingredient is tainted, the whole dish is at risk. and we are adding hundreds of ingredients to our software tools, like hundreds of ingredients in or let's say a lot of dependencies, or a lot of open source on our application, on our code. So we have these huge dependencies on open source, and attackers know it. So let's move into our slide. So modern malware does not exploit software; it exploits trust. So uh, in the past, most security incidents have followed a familiar pattern. What it does is that he find a vulnerability, then he exploits it, then also you compromise the system, then eventually it get detected, then apply a patch. So this was like the classic cycle. Tools and teams focus heavily on SVEs and known exploits, and security scanners looks for signatures of non-malware and assume that if none were found, the software are clean. So this approach struggles with today's threats. Now, looking at the new modern the new mental model, the new model doesn't like bother with the initial barrier at all. It looks more like this. So it goes from the trust to automation to propagation, artifacts, then silent persistency. So the attacker first goal is to appear trustworthy. This could mean like using a stolen maintainer credential to publish a package or adding malicious code to a popular library. The exploit uh, They exploit the fact that we trust update and new package by default in our automated system. So once the malicious component is out there, our automation pulls it in CI/CD pipeline, auto fetch dependency, update get installed without like human actually reviewing it. The malware spread rapidly because our tools are designed to actually save us time, not like suspect foul play. Now looking at the um, propagation with uh, with with automation, a single malicious release can propagate into thousands of projects almost instantly. Think of a bad npm package version. As soon as as soon as it got published, any build fetching the latest version gets that malware. So it propagates through the ecosystem at the speed of DevOps. Now, so here's the thing: the malicious code makes its way into the build artifact, the final barrier, or the container. So at this point, it's embedded inside what looks like a perfectly normal application or update. So the artifact then get delivered to user or deployed to server, carrying the malicious payload within, which like which we infiltrate or like download user informations and then move from there. So we talk about silent persistency. Now, the malware can persist silently since it was introduced via normal build process. It may actually not trigger any runtime alarm immediately. It might sit dominant until a certain condition is met, or it might infiltrate data under the radar. No exploits, no loud signal, just lives in our system. So this persistence is hard. I would say it's very, very hard to detect because everything appears legitimate. The code pass all the check by virtue of being part of the trusted on the trusted build. Now, in this new model, there's no software vulnerability being exploited at all. The vulnerability is our overtrust in the supply chain. So attackers realize they can ride that trust from inside. So instead of breaking in from outside, they will just slip in this from the side window. So with the new model, security teams need to pivot. We must treat also we must treat software pipeline and open source component as part of our threat model. The old assumption no longer hold. Let's go to the next slide. Okay. Now, in September 2025, an attack we call Phantom Raven hit the Node.js ecosystem. So attackers published over 120 malicious npm package, which together get around like 100,000 downloads before being discovered. Here's the clever part. Those packages use remote dynamic dependencies to pull in malicious code at install time. This means they fetch evil code uh, while on run, making them harder to actually detect through static analysis. This was actually targeted strike, but an eye opener. Now, looking at Shehud, so not even a month later, we saw Shehud another wave of malicious npm package. This time, over 500 plus package were compromised, and shockingly, they were getting over 2 billion weekly downloads. So, how is that possible? The attack took over account of trusted maintenance on npm. So, essentially, they stole the key to the library, which is like well-known libraries, and then push malicious updates because these were trusted package updated by trusted maintainers. So everyone automation put the update in. So it was the new model in action at massive scale. Now we're looking at version 2, which is the sharehold v2. By November 2025, the same group had to they expanded into the Maven Central repository, which is the Java ecosystem, showing this is not just a JavaScript problem. So 800 plus malicious package were published, and um, why download count like 2 millions weekly. We are lower than the NPM cases. So it proved that cross-language supply chain attacks are a reality. So an attackers in one ecosystem can inspire your copycat in another. So no language or package manager is inherently safe from this. So looking at this example, it shows how an attacker can poison the way for countless projects in one go. So instead of like hijacking one company at a time, so this approach breaches thousands of companies at once via their code supply chain. So also at least think about what those numbers mean. If you are using one of these like 500 npm package in Shehod, your application was essentially infected the moment you run npm install. And the worst part here is that it might have been automated build that did it with no human ever actually noticing that this uh, evil code is being added. So they were crafted to avoid immediate suspension. So if you look at in Phantom Raven, the use of remote dependencies meant the malicious payload wasn't even in the package at publish time. So it will actually fetch later. So like the malicious code wasn't on the runtime, which was actually fetched later. So now seeing this attack, a fair question is this: what's the goal? Why go to all this trouble to slip malware into our open system or into our open source? Sorry. So here's the thing: once attackers slip malware into your build process, they often go straight for the keys and secrets. For example, they could target your GitHub, GitLab, Azure DevOps, Jenkins, personal access token. So, and also cloud keys like AWS, IMS secrets, your Azure secrets. With those, they can access code repository or even leave cloud environments. They also look for automation and deployment token like the credentials your CI system use to deploy application or containers. So once they steal this information, attacker can publish malicious code to your production or spin up resources in your cloud if um, if there is no drift if you didn't set up the drift detection on your pipeline. So if they steal your code, if they see your code signing certificate or key, they can produce malicious updates that look officially signed by you. Now, looking at sensitive data, like database connection string and API keys are also uh, targeted. Those uh, those can actually lead directly to data breach if the attacker use them to pull data from your database or call internal APIs. So it's not just about the I'll say it's not just about the pipeline. It can also lead to like customer data loss or further exploit in your production system. So okay, that's So here's the thing: given that attackers can steal such critical assets, why aren't our existing security tools fetching this? We have like scanners, CI checks, even malware detection tools. Why did those big attacks slide by? So we're going to explore the answer here on the why traditional AppSec is blind in modern malware. So here's the thing: many AppSec programs still operate under certain assumption. I would say like call it an illusion of safety. They assume dependencies are being build pipelines are I would say inheritedly trusted, and if your code build passes tests, the artifacts are safe. So in other words, if there's no known vulnerability or error, everything actually must be fine. So these assumptions are reasonable ones, but attackers have learned to exploit them. Now we're looking at malware conditional behavior. Here's the thing: the reality is modern malware is often designed to actually hide under exactly those conditions. It activates only under specific condition, maybe only in CI/CD or only when certain environment variables are present. So, for example, I'll say in a developer's local test, nothing is going to happen there. So it's going to keep silent. But in the CI environment or when the code is deployed in the cloud, suddenly the payload is going to trigger. So this conditional environment, I'll say this behavior is a big reason traditional scanner miss it. So they're not like executing code in the right context to see the bad behavior. So look, you see no known signature. Traditional security tools rely on known bad pattern, signatures, known malicious domain, or previously reported SVEs. If malware is custom to your environment, it won't match a known signature. And if it's a novel attack, there is obviously no SVE yet. So tools that actually look only for SVEs or known bad hashes comes up actually blend empty. Now I'm looking at blind spots in our pipeline. So security testing often happens as actually the wrong place. We scan code repo and we scan running application, but rarely like scan the build process itself. We just trust it. That's exactly where malware is actually hidden in that build spot between Git clone and deployment. So, for example, a dependencies gets put in and runs some install scripts. many security teams aren't watching that steps closely. So which we are going to like show in demo or technical walkthrough after this slide. So all this actually means that traditional AppSec can be essentially blind to those threats. It's like having a security. So look at this analogy now. Analogy. It's like having a security camera that only points at the front door, while the thief is actually coming through a side window. So if our tools assume everything we let in is fine, we'll miss the malicious behavior that piggybacks on our trusted process. Okay. The new malware model for 2026, which is AI-driven attack. According to recent survey, 60% of IT leaders considers AI-generated attack even more dangerous than ransomware. Think about that. Ransomware has been one of the most biggest threats in the past decades, and and leaders believe AI-driven malware could be even be the worst. So here's the thing: what do we mean by AI? AI generated or AI malware? We mean malicious code that either written by AI or behaves in an autonomous or intelligent way. This malware has a this malware have a human-like structure to its code, making it even hard to distinguish from normal code. It can pass manual code reviews because it doesn't do obvious bad things at the first glance. So it doesn't like behave on the first time. So it's going to like look professional written. So looking at context aware, AI malware can be context aware as well. It knows if it is in a CI environment or a tested environment, and we only execute each payload under the right condition. So you might actually check, am I on a developer's laptop or on a GitHub action or a Jenkins server, and behave accordingly. This makes it virtually invisible during the normal development and also Q&A. So such malware might also be autonomously mutating. This means it can change itself like slightly or try different method over time. If the first attempt to run the malicious code fails, it can then try again in a different way. So I want you to think of it like an automated hacker that keeps probing, but all contained in a piece of code. So it can even like republish new version of itself with a tweak to evade detection. So here's the thing. We are essentially looking at malware that can actually like that can operate like an agent, decide when to strike, adapt to its environment, and even attempt to spread or persist without like direct human control. So uh, I would say this is a leap in sophistication, and also it's not just a piece of code waiting to run. It's a code that actively tries to outsmart our defense. So the game is changing. So how do we defend our pipeline and software supply chain against these advanced threats? So this is where we are going to introduce Cygene's early warning early warning system. Hygienist early warning service works by continuously like scanning open source package and dependencies in real time. So instead of waiting for vulnerability report or an incident, it's always watching the new code as it enters your environment or even before that. So in public repository, even before that in a public repository. So this is like having a dedicated security guard for your supply chain on duty 247. So Sagini looks at code behavior and pattern, not just SVEs. It uses advanced static analysis and even machine learning to detect suspicious code in packages, things like attempts to read environment variables or open network connection where they aren't expected. So essentially, it does a behavior code analysis to spot zero-day malware. So this means it can catch malicious intent even if the code have never been seen before. So here's the thing: why Sargent is constantly scanning the public register. Uh, when Sargent finds a package that looks malicious or even just highly suspicious, the first step is to alert the user on email or on the UI or on the Slack you're actually using. So after that, after that, the package, after that, the second thing that is going to be done is quarantine. So that package is immediately like flagged and isolated. So it won't be allowed to run in your build or in your deployment. It prevents the potential malware from being damaged while further analysis is done. So from quarantine, the next thing is security engineer review. So uh, from quarantine is going to go through a code review by your security engineer, DevSecOps, or security team. So I want you to think of this as a second layer of defense. A human or an expert system examine the flag code to verify if it's truly is malicious. So this helps eliminate like false positive and build confidence. So once confirmed as malware, we then get confirmation again by the public register. It means that Sargini coordinates with the maintainers of official package registry like the NPM, Pipe, Maven to report the malicious package. So often, when such confirmation happens, the register will then remove the bad package so no one else can download it. So this collaboration is the key to protecting the broader communities as well, not just one organization. It's like alerting the whole neighborhood a bad actor is actually identified. So finally, hygiene then ensure disposal and public disclosure. Um, so this means the malicious component is now disposed and disclosed. Disclosure is actually made. So, for instance, adding it, Surgeon will then add it to the extended threat database they have. So, this transparency helps others organizations to learn about the malware. Think of it as like uh, inoculating the community. So by disclosing these threats, Sargent helps others to avoid issues. So you can actually like go to the database and check out this malware and know or what's actually affected and what's actually in there. So now that you see the overall process, uh, so let's talk about what makes Sargent approach so effective in the and unique for DevSecOps team. So zero day detection behavioral code analysis. So Sagini use behavioral code analysis to catch zero-day malware. So which means it looks at how the code acts or what it intend to do, not just whether it match a known vulnerability. So for example, if a package code tries to collect or your Azure or AWS credentials and send them out, that's suspicious by behavior alone. So even if no SV or signature exists for it, so actually we catch that. This direct counter the new malware strategy. So now, Real-time threat detection and blocking. Importantly, this detection happens in real time. Certainly can be integrated into your build pipelines or artifact repository. The moment a build pulls in a new dependencies, Sagini will analyze it. If it is malicious, it can automatically block that package from executing or being used. So they have guardrail that it follows. So this is what we call the early warning in action. The team gets alerted and the threat is stopped before it actually cause more harm. So continuous scanning also and also uh, Sagini runs like continuously in the background, which is crucial given the volume of open source updates. So it's not a one-time scan. Every new version, every new package gets checked. So this actually aligns perfectly with the CI/CD practice, and also it's DevSecOps friendly because it automates and integrates with tools developers use. Also, Cygene also draws extended vulnerability database, which we already talked about, non-CV SV threat intel. So it's not like limited to the official SV list, which we know can be slow or incomplete. So Cygene include community findings, malware database, and its own research. We're going to also go through that technical walkthrough. We're going to see the database, see the malware being stored after the slide. So from from a from a DevSecOps perspective, Cygen is designed to fit in into our existing workflow. It can integrate with our pipeline, our Jenkins, GitHub Action, Azure DevOps, GitLab as a step that can scan dependencies. It can also integrate with artifact repository to scan new packages on injection. The idea is to embed security without adding heavy manual steps, so developers and security engineers get protection by default. So to actually really cement on how this works, let's walk through a scenario of Signally warning action. After that, we're going to jump into a live demo to see the interface and also the workflow. So um, imagine a developer on your teams add a new open source library to your project, maybe a login library from npm that looks useful. They update the project config, which is the package.json, uh, and push the change, which trigger the CI/CD pipeline. So the moment the CI/CD pipeline tries to fetch this new library, Sagene kicks in and scans the package codes. Let's say the library version was unfortunately a compromised one. Sagene static analysis quickly flags that the code is trying something odd, like for example, reading environment variables and also sending data to an external URL. Then Sagene will quarantine the package and immediately flag the build. The build might be stopped, or that component is immediately flags the build. Yeah. So as a DevOps engineer, you get, or as a DevSecOps engineer, or as a security engineer, you get an alert. You understand, from the UI or from the email, saying what you actually found. So as the security engineer, you receive the data from Sagini, which line of code are actually suspicious, what the package was trying to do. They will quickly review and confirm, yeah, this is malicious. It's trying to steal AWS or Azure keys from the build environment. So I want you to think of Sagini as a meta detector at the entrance of your pipeline. Every package, every package goes through it. If it finds a hidden weapon, which is like the malicious code, it stops that package from entering and raises an alarm. You take the weapon away and you let the normal flow continue. Without the detector, that weapon would have made it inside unchecked. With Hygiene, you disarm the attackers before they get through the door. So now that we have walked through how it works in theory, so let's see it for real. So I'm going to switch over a live demo of Hygiene early warning system. We'll look at the dashboard, how alert appears, and show an example of a malicious package detection so you can see the speed and the detail it actually provides. So so this is what Hygiene UI actually looks like, and inside it we're going to remember why we talk about the malicious database where any malicious code or any dependencies that is actually malicious is actually found and being stored. So this is the database, and inside the database you'll be able to, go through the malicious code dependencies that has actually been tempered, and so you can as well filter the quarantine one, so which is actually going to load and be able to see. Uh, So this project, if you see, look at our projects, this project is what we are going to work on. So we are going to run the we are going to go through the code. We're going to go on GitHub, we're going to go through the code, we're going to add a virus, and we're going to see how we're actually going to detect this malicious, so we're going to add virus on the runtime, on the pipeline, and also on the package JSON, package log.json, we're going to add it there. Then we'll see how the pipeline actually runs and how you actually find these and what you actually found. So this is the guardrail for malicious dependent guardrail, and on we'll start with the application code. So when we go to the application code, we'll go to the package log JSON. So we're going to add a virus, like I said, so that we see how it actually simulated. So on over here, I'll be able to add the virus here. After we have added the virus on the package log JSON, we're going to add a command that fetch virus on when the pipeline is actually triggered. So we're going to commit the change. Once we're done with committing the change, we'll go to our pipeline. So when you go to our workflow, we go to build. So we're going to add the virus. So this code, what it does is that it downloads this it downloads malicious code at runtime. So when we go to looking at this, so uh, we're going to add it over here. And we are going to commit the change. So when we go to risk into see the last scan, which is like 6 hours ago. So we have added this virus. So we're going to run the workflow and see what we actually found. So I'll go to action. Now we already see our scan went through before. So we're going to run the workflow. Let's reload the page. So yeah, so the workflow is running. Is the Sargent scanner is scanning. Um, so scanning. So here's what's gonna happen. Because of the guard thread that is actually set up and everything. Um, once it detects the virus, so instead of our build to actually go through, it's going to stop the build. It's going to stop the build, and it's going to show us what you actually found on the build. So you can see the build have actually failed, and this is the finding. The suspicious dependency, um, the malware as well. So let's go to Sagini UI, and when we go to the project, and go to manage scan. So the UI is going to update with the latest scan. It's going to update with us, and we're going to go through what the malicious code, if it actually dictates the virus we added on package.json, package log.json, and also on our workflow. So we'll see how effective it is. You have seen how it didn't let the build pipeline go through. It actually dictated the suspicious dependencies and also the malware, and it was able to reject the build. So it's going to update us with the UI on the UI here, and we are going to go through the the findings and see what you actually found. And that's how I actually scans and see how what it actually finds and see how effective it actually is, if it actually does, because we talk about all these modern threat detection, we talk about modern AppSec, uh, not actually finding rate threats on time, or we talk about early worm detection, which modern AppSec doesn't actually find on real time. So we talked about this. So now we are to see, we have seen the walkthrough where you actually stop the pipeline. So we're going to see if you actually see the informations, and yeah, we'll be able to see in action. And it take a little bit time. So we'll see what's up to a little bit more. So be able to see it all together. We all want to see it, right? So yeah. So the job is completed. We see success. So let's go to risk. So on the risk, we'll see we'll see okay, this is the blacklisted potential malware components, which we malware dependency and npm, which we actually found earlier. which we added on also on this place. Okay. So you remember the virus we added on um not the viral, but what fetches the viral, download the virus on our runtime. So we added it on our CI/CD build, and it actually dictates it, and we're able to see it. So the two viruses actually found, and so this is what real-time detection and Cygene early warn malware detection looks like, and how effective it actually is. So and like I explained earlier on the package database. So let's say, for example, you are using for your malware detection, and you are notified about a malicious source code or package you want to download, or was actually new updated, and you actually be notified about it and you're aware about it. So let's say, for example, you are not you just want to explore other reported malicious code you just want to be aware of, you can as well come to the database and as well go through it and be able to see everything here. So yeah, if you have any question, you can. But we all have seen the action in real life. We have run through the technical walkthrough where we on our GitHub action we're able to on our code we intentionally added virus on our package log.json and also on our CI/CD pipeline, and we wanted to see how it can actually detect these malicious dependencies and malware. So we run the pipeline and was able to. Our pipeline was unsuccessful, which it shows what was actually the findings. So we went to the UI and the scan was completed, and we were able to find the virus, and that's how modern app or that's how effective Sagent actually is on finding these malicious code and malware. So if you have any question you want to ask, feel free to drop it on the chat to be able to attend to question. Someone ask, how can I get that documentation? You'll be able to um, you can be able to get the documentation. I'll say send us an email on info@nimbuscompute.co.uk or reach out to Cygene. Go to the website www.cygene.io and you'll be able to get the documentation, also get demo as well on the product and see how effective it is. So I think that's the only question we have. Thank you everyone for joining. I hope you were able to learn one or two and see how everything actually works out. So thank you all for joining.